Sorry, just yeah, the confusion. Just give me maybe. Okay, are people able to hear my sound now on YouTube as well as on Unacademy? Is it working fine on YouTube now? Okay, yeah. Apologies for the issue. Yeah, I think it should work fine on YouTube now as well. In case there's any issue, I'll keep monitoring the chat. Like somebody can post it here, but yeah, I think it should work fine. Okay, so like coming back to the definition, like we need to define what is called the centroid of a tree. Okay, so the centroid, I've shared my slides, right? Yeah. Okay, so what is a centroid? A centroid is basically a node whose removal would split the given tree into a forest of trees where each of the resulting tree contains no more than n by 2 nodes. Okay, so there's a lot happening in this single sentence. So what we're trying to say is that any tree can have multiple nodes. Like say uh, this is a tree, suppose. Okay, suppose this is a tree. Here, the way I'm drawing a tree is that so any tree can be a rooted tree or unrooted tree. If you pick a node and try to root the tree on that node, you get what are called subtrees, right? So suppose I pick this node arbitrarily and root the tree on this node, and and then I get these I get these subtrees, uh, I get these subtrees of different sizes. A centroid is basically a node such that if you root the tree on that node, every subtree would have a size less than n by 2. N by 2. Okay. So, sorry. So what exactly is happening here? That it is same as what is written in this definition. That given a tree with n nodes, a centroid is a node whose removal would split the given tree into a forest of trees where each of the resulting tree contains no more than n by 2 nodes. Okay. Like this is same as saying that if you if you if you are able to find a node in the given tree and root the given tree on that node such that every subtree formed has a size less than n by 2, because what would happen if you remove this node? If you remove this node, it means that you'll also remove these edges, right? Removal of a node from a tree means that you remove the node and the adjacent edges for that node. So then you will get every subtree will become an independent tree, and the definition says that the size of each of these subtrees should be less than n by 2, or the new trees which are formed should be less than n by 2. Okay, so this is the definition of a centroid. Like we still don't know how to find one. We don't know whether one exists or not. We haven't proved anything yet, but this is the definition, that if you are able to find a node in the given tree such that if you remove that node, the new subtrees which are formed, every subtree would have a size less than n by 2. Or like if you forget about removing, if you root the given tree on that node, every subtree for that every subtree connected to this particular node would have a size less than n by 2. The size of this tree would be less than n by 2, less than n by 2, and so on and so forth. Okay, so this is the definition of the centroid. Now I have a quick question for you guys. Given this tree, what would be the centroid of this tree? Okay. First, of course, like, does there exist a centroid? And if yes, which node is the centroid? I can tell you guys that a centroid exists in this tree. You guys should focus on how do you find the centroid of this tree. Okay. So if you just try to look at it and compute, the total number of nodes in this tree are 15, because like we've already done the numbering, like nodes are already numbered. So this tree has 15 nodes. Okay, 15 by 2 is 7, integer division. So can you find a node such that every subtree attached to that node has size less than or equal to 7? There are 4 options given, A, B, C, D, 5, 8, 9, and 2. I'll quickly create a poll, and, and maybe you guys can answer. Okay, so I've created a poll. You guys can answer the poll. I'm showing you the diagram once again. Can you guys find the centroid of this tree? Again, the centroid is a node such that all the subtrees which are attached to centroid have size less than n by 2. Okay, have all of you answered the poll? Let's quickly look at the poll results. Yeah, so all of you, majority of you have answered B, which is the correct answer. B is node 8. Okay, so node 8 is the correct answer. Why? Because if you look at both the subtrees which are formed, if you root this tree at node 8, the first subtree would be this, and the second subtree would be this. And both of these subtrees would have less than equal to 7 nodes. 1, 2, 3, 4, 5, 6, 7. And here also you have 3 plus 1, 4 plus 3, 7. So both of these subtrees would have 7 nodes. And if you look at any other node, there would be a subtree which has more than 7 nodes. Okay. So node 8 is the centroid of the given tree. So now, like, we have defined what a centroid is. We have also looked at a sample example. But the next question is that, first, does every tree have a centroid? Whatever the given, like whatever the shape of the tree might be, can we prove that the centroid of the tree always exists? And if we can prove this, like the second question would be that how do we find the centroid? Okay, so these two are the most obvious next questions that we would ask. The first question is that does the centroid always exists? And the answer to this question is yes. For any given tree, the centroid always exists, and this theorem was proved by Jordan in 1869. And how do you prove it? So it is not hard to see. Like you can even not like you can not know this proof and still try to come up with a proof yourself. It is that trivial. So suppose you look at this example. Okay. Suppose you are given a tree. There is another subtree hanging down from node 11, another subtree hanging down from node 10, and another small subtree is hanging down from nodes 153. Okay. Suppose like this is any arbitrary tree which is given to you. I've drawn only a few nodes, but suppose there are even more nodes. Okay. Suppose you start with any arbitrary node. In this case, I start with node 9. Sorry. So suppose I start with any arbitrary node in the given tree and I ask, is this node a centroid? I already know how to answer that question. Why? Because this node would be a centroid if the size, the subtree size of each of these subtrees would be less than equal to n by 2. Only then would the given node be a centroid. So I can always ask the question whether this given node is a centroid or not. I know how to answer it. Suppose this node is the centroid. Then we are done. We already found a centroid. But if not, okay, if this node is not a centroid, we claim that there will only be a single subtree whose size will be more than n by 2. Okay. When would this node be a centroid? This node would be a centroid all of these sorry if all of these subtrees have a size less than equal to n by 2. But if node 9 is not a centroid, it means that there exists at least one subtree whose size is more than n by 2, right? This is like an obvious statement. Now, can there exist more than one subtrees with size like greater than n by 2? No. Why? Because if you add the subtree sizes, the total should be less than equal to n. So therefore, there will exist exactly one subtree, exactly one subtree with size more than n by 2, right? So suppose in this case that subtree was node 8, like the subtree rooted on node 8. Okay. So suppose this is the subtree with size greater than n by 2. Assuming that node 9 is not a centroid. What can we do? We can now recurse such that we make node 8 our root. Like we modify our root and root the given tree on node 8 and ask the question again. Okay, so now node 8 became my root. Node 1, node 5, and node 3 have their subtrees. No, and like node 11 and node also have their subtrees. Okay, so now like this is the picture. So now the claim is that if you keep doing this procedure, eventually you will hit a node which is the centroid. Okay, and why is that? Basically, if you try to look at this subtree, can it happen? Can it happen that the size of this whole subtree is greater than n by 2? Because if this can happen, then based on our procedure, from node 8, again we will come back to node 9. And this will keep happening all the time. And we will be stuck in an infinite loop, right? So, is it possible that the subtree size of this whole subtree is more than n by 2? No. No, it's not possible. Why? If you look at this subtree size, okay, we know that, so we have two different parts of the given tree here. We know that this part was more than n by 2. Okay. We know that this particular part was more than n by 2. And how do we know that? We know that because that is the reason we recursively came on node 8 from node 9. Originally we were at node 9 and we recursively came on node 8 because we said that the subtree at node 8 has size more than n by 2. So therefore, if the subtree size of this whole part is more than n by 2, the subtree size of this part, like basically the subtree rooted at node 9, has to be less than n by 2, right? Has to be less than n by 2. So here we have shown that this subtree is less than n by 2. And therefore we can say that, like whenever we move from node from a given, like whenever we change the root of our tree using this procedure, whenever we change the root of our tree, we can be sure that we will never go back. Like we will never go from node 8 to node 9 again. Like we can either node 8 will be the centroid, or we will end up recursing either on node 1 or node 5 or node 3. We will never go back again on node 5. Okay. So this proves that in this given procedure you always move to a new node. You never come back to a visited node. And since the number of nodes are bounded, like since the total number of nodes are n, you will eventually hit a node where you neither come back to the previous node nor go ahead to another node. And therefore the procedure will definitely end, and when this procedure ends, you will have your centroid with you. Okay. So like if you look at the official proof statement, it says that you start with any arbitrary vertex and check whether it satisfies the property of being a centroid. Okay. So suppose I started with vertex 9 and I checked whether vertex 9 is a centroid. If yes, then we are done. Otherwise, there exists only one adjacent subtree with more than n by 2 nodes. In this case, the adjacent subtree with more than n by 2 nodes was the subtree rooted at node 8. Okay, this subtree. So then we consider the adjacent vertex u. In this case, the vertex u is vertex 8 that we consider in that subtree and apply the same argument. And what was the argument? That check whether node 8 is a centroid. If yes, we are done. If not, look at the adjacent vertices and look at the subtree with more than n by 2 nodes and recurse there. And the reason this works is that we can be sure that from the node which we came to, like from the from the node where we came to the current node, we will never be going back again. Going back is not possible because the size of this whole subtree will always be less than n by 2. Okay. Is this proof clear to everybody? Any doubt so far? Please do a thumbs up if it is clear, and then maybe we can move ahead. Okay, great. Sorry. Yeah. Okay. So now we know that for any tree, a centroid always exists, and we have also found a way to find a centroid. Like we have also discussed a way to find the centroid of a tree. And what is that way? Start with any arbitrary node, keep recursing in the subtree which has size more than n by 2. If no such subtree exists, then the current node is the centroid. Just return it. Okay. So the next part is that how do you decompose the original tree to get the centroid tree? Okay. Now we know that for a given tree, how do we find the centroid of that tree? The next part is the centroid decomposition part, that you end up decomposing the original tree and you construct a new tree which we called the centroid tree. Okay. So let's look at the procedure, uh, like an outline of the procedure, and then like we'll discuss more and build more intuition of what exactly is happening. Okay, but just purely in terms of an algorithmic procedure of what exactly is happening, what we do is that we have a procedure called decompose, which takes an arbitrary vertex, okay, say root, and it takes the centroid of the parent. Yeah, just forget about it right now. So the first procedure is that like you give any arbitrary vertex for the given tree. You have a tree. Suppose you root the tree at node one. So you call decompose one. Okay. The first thing is that you find the centroid of this tree. We know how to find the centroid of a given tree. We already know this. Okay. So you find the centroid of the given tree. Now you have the centroid. Suppose this is the centroid of the given tree, and suppose like these are the subtrees. If you root the given tree on the centroid, suppose these are subtrees. What you do is you remove this centroid and the corresponding edges. So you have a forest of trees now. You have a forest of small trees. And you recursively call this decompose procedure on each of these forests. Assume that the decompose procedure returns a tree. Okay, the decompose procedure returns a new centroid tree. What you do is that you attach the centroid tree returned by this subtree here. This was the centroid C. This was centroid C of the original tree. Similarly, you attach the centroid tree returned from the second subtree here, and you attach. Sorry, say you attach the centroid tree of the third subtree here. Okay. So basically, what is happening is that if, like, as my centroid parent, I pass on the centroid node of the previous component. Like the like originally I'm talking about the whole tree. Like so, the centroid parent is -1. But suppose I have found a centroid now for my given tree. In the first iteration, like this component will be -1, so we don't enter this if condition, and then we iterate on all the adjacent edges and vertices of this centroid. So for every adjacent edge and adjacent vertex for the given centroid, I delete that edge from the graph and I call decompose on the adjacent vertex, and I pass my current centroid as the parent of the centroid tree, which will be formed by this recursive decompose call. Okay, so every recursive decompose call will return me a small tree, and I attach that tree on the current centroid node. Okay, so let's take a look at the pictures once and try to see what exactly is happening. Okay, the idea is that given a tree, you find the centroid of that tree. You Okay, so I mean, suppose you find the centroid, you take this centroid node and you make it the root of a new tree. You make it the root of a new tree called the centroid tree, and and you recursively compute the centroid tree from each of these subtrees and attach the t primes as children of this root. Okay, let's take a look at an example, and I think it would be more clear. So, for example, you have the same tree given again, and you want to I mean, this is the original tree. This is the original tree which is given to you. Okay. and you want to decompose it and build the centroid tree. So the question is that which node in the like from the original tree will become the root node of the centroid tree. Okay, which node from the original tree will become the root node of the centroid tree. Notice that I've told you that the root node is always the centroid of the given component. So whenever you call decompose, it a rooted tree, returns a rooted tree with centroid of the original tree as the root. Okay. So the decompose method always returns a rooted tree, which is the centroid tree, rooted on a particular node, and the center of the original tree becomes the root node of this rooted tree. Okay, this is what the decompose method does. And now I ask you the question that which node from the given tree, like from the given original tree, will become the centroid, like will become the root node of the centroid tree. Okay, that is the question. I'll again quickly create a poll and maybe you guys can answer. I quickly create a poll and you guys can answer. The question again is which node will become the root node of the centroid tree given that the original tree is as shown on the left side. Okay. And we know that whenever you call decompose, it returns a rooted tree with centroid of the original tree as the root. Yeah. So majority of you have answered C, which is the correct answer. And why is that? Why is that the case? Because we know that node C is 8, and we know that 8 is the centroid of the given tree. We know that in the given tree, 8 is the centroid. So, so when you call decompose on the given tree T, like let this whole tree be shown as T. Like when you call decompose on the given tree T, it finds, like what does it do? The first step is to find the centroid. So it finds the centroid, node 8 is the centroid, and it makes node 8 the root node of the centroid tree. And then you remove this node 8 from the original tree. So you remove this node 8 from the original tree. You remove these edges. Now what do you have? You have two different subtrees. A subtree on the left side and a subtree on the right side. And you recursively call decompose on these two subtrees. Okay? Like this is what we do. That we like let the left tree be T1 and right tree be T2. We recursively call decompose T1, decompose T2. And these are independent subproblems in a way because you have already removed this edge. Like this edge does not exist anymore. You find the centroid, remove the corresponding edges, you get a bunch of smaller trees. You have a forest of trees now. You call decompose on each of the individual subtrees. Again, the decompose method returns the rooted tree with the centroid as the root. But now the decompose method is called on T1. So the decompose T1 will return a rooted centroid tree with centroid of T1 as the root. The centroid of T1 as the root. Okay. So suppose we have another question that how many children nodes would node 8 have in the centroid tree? So as we discussed earlier, how would the centroid tree look like? You will call decompose on T. This whole is T. This part is T1 and this part is T2. You call decompose on T. Decompose on T will find centroid, which is node 8, and make it the root. So we have node 8 as the root node of the centroid tree. This we already saw in the previous question. Okay. The third step would be to edges, delete the adjacent edges, and call decompose T1 and decompose T2, right? So you call decompose on T1, which is just this much. Like this is an independent smaller tree, T1. Okay. You call decompose on T1, and similarly, you call decompose on T2, which is an independent smaller tree, like highlighted by this black boundary. Okay. So you call decompose on T1 and T2, and you attach that subtrees returned by these decomposed T1 and decomposed T2 on the node 8. So node 8 will have a subtree here, which is returned by decomposed T1, and a subtree here, which is returned by decomposed T2, right? So the question is that how many children nodes would node 8 have in the centroid tree? And this is the picture of the centroid tree which I'm showing you. I'll quickly create a poll. I'll quickly create a poll, and then maybe I'll take a small break to answer the questions which are currently in the chat box. So the poll is that how many children nodes would node 8 have in the centroid tree? Okay. So in the centroid tree, again I'm repeating. The first step is we call decompose on the whole tree. It finds the centroid, which is node 8. It creates it the root of the centroid tree. This is the root. And then it removes the edges and calls decompose on the smaller subtrees which are formed. In this case, the subtree formed are T1 and T2. So we call decompose T1, decompose T2, and we attach the trees returned by these recursive calls on node 8. So I've attached decompose T1 subtree on node 8 and decompose T2 subtree on node 8. So like what would be the answer of this question? B, exactly. So most of you have answered B, which is the correct answer, that node 8 will have two children in the centroid tree. Okay. And to give you guys a complete picture, this is how the centroid tree would look like for the original tree. Let's come to this, but there are some questions in the chat, so let's quickly look at the questions. I think Kunal is also trying to answer some of the questions already. Shivam asked that what will be the roots of T1 and T2 in the decompose function. So T1, the root for T1 would be the centroid of T1. The root for T2 would be centroid of T2. Yeah. So the root pass the first time would be like -1, because like for the whole tree there's no parent which exists. Can there be more than one centroid? Yes. Like there can be at most two centroids. Yeah, I think Lakshya maybe has joined late. I've already discussed the definition of centroid. I mean, the centroid is a node which, if removed, will split your tree into smaller subtrees, each of which has size less than n by 2. Okay. Okay. So coming back to our decomposition, this is how, like, given the original tree, if you call the decompose function on this original tree, this is the centroid tree that you get. And if we quickly try to look at what is happening, you first call decompose on the whole tree. For whole tree, we find the centroid of the whole tree. We make this centroid the root node, and then we remove the edges corresponding to this centroid. Like we remove the adjacent edges, we get two smaller subtrees, subtree one, subtree two. We recursively call decompose, like we call decompose on these smaller subtrees. Okay, so decompose for T1 will find the centroid for T1, which is node 2. Why is node 2 the centroid? Because like total number of nodes in this part are 7. If you remove node 2, you get subtree with maximum size 3. So therefore node 2 is your centroid. Okay. You find node 2, you remove the corresponding edges, you get 4 smaller subtrees. You get 4 smaller subtrees. You recursively call decompose on these 4 smaller subtrees. For node 1, like there's nothing to do now. So you just return. For node 3, nothing to do, return. Node 4, nothing to do, return. Node 6, uh, like for this particular component, like the decompose function will find the centroid, which is node 6, remove the edges, and recursively go to node 5 and node 7. Again, single nodes, like nothing to do, return. So if you try to look to like if you try to visualize this recursive procedure in your head, if you start from bottom up, what happens is that like node 7 and 5 were single nodes. Like, like, I mean, by the time we called decompose on like on these smaller nodes, I mean the subtree size was one basically. So like there were only single nodes. So therefore, these are the subtrees returned by decompose on 7 and 5. You attach both of them to node 6 because node 6 had, like when you remove node 6, there were two smaller subtrees formed. Like one with node 5 and one with node 7. Like this is the yellow part which I'm talking about. So you attach them to node 6. Similarly, for node 2, you attach all the four children. Like all the. So every subtree formed when you remove a node will become the children, like will form a child of that node in the centroid tree. So if you remove 2, you get 4 subtrees 1, 3, 4, and this one. So all these 4 subtrees will become 4 children of node 2 in the centroid tree. Notice that by the time you are doing this edge has already been deleted. Like when you come at node 2, you are only looking at the subtree which is highlighted by the black region, which is the T1 subtree. Because you're going bottom up. Every time you recurse, you actually delete an edge and then recurse. Okay, so similarly for node 8, the left part, like the T1 subtree transformed into this centroid tree, the T2 subtree transformed into this centroid tree. You have the centroid trees, say CT1 and CT2, and you attach both of them to the root node, and this becomes your centroid tree of the original tree. Okay, like you can also visualize the procedure on the right side. Again, same thing will happen. Like this will be your centroid for the black region, and therefore you attach it as the child of the node 8, and you recursively compute centroids of these smaller subtrees. Like for this subtree, the centroid will be node 10, similarly node 13, and you attach them as children of node 9. Okay. So this is how you construct the centroid tree from the original tree. Like this is the most important part, I think. Like for this lecture, like how do you decompose the original tree to get the centroid tree? So like you have like how many, like what are the doubts? Like this is the time to ask your doubts if you have any. Can centroids be found? We will look at the implementation and we will discuss the time complexities. Like so, don't worry about it right now. But in like just in terms of what exactly is happening, like what are the doubts? So we will visit only unvisited nodes. Like let's not worry about the implementation, Lakshay. Again, uh, like we will look at the implementation right now. Just think about what exactly is happening. Okay. So what exactly is happening is that you first find the centroid, you delete the edges corresponding to the centroid. You delete the edges, you get smaller subtrees. You recursively call the decompose function on each of the smaller subtrees. Again, like for this small subtree, when you call decompose, you find the centroid, delete the edges, recursively call decompose on the smaller subtrees formed. Okay, and so on and so forth. Okay, doubts, like this is the time to ask the doubts. Like if it's not clear what exactly is happening, how exactly the centroid tree is being computed from the original tree, like this is the time to ask. Like it is very important to understand that the centroid tree has a very specific structure, but this is not the same as the original tree. The original tree and the centroid tree are very different. The centroid tree has all the nodes of the original tree. Every node in the original tree becomes a node in the centroid tree at some point of time, like during this decomposition procedure. But if you see, like their shapes are very different. For example, there is an edge between node 8 and node 2, but there is no edge between node 8 and node 2 in the original tree. But there is an edge between node 8 and node 2 in the centroid tree. So the structure of these two trees are very different. But of course, like centroid tree, like we will look further of what it represents and how it is useful. But it can be very powerful to build this centroid tree. Like we will also look at some of its properties. But what exactly is happening? Like how exactly we are building like what is being represented by the centroid tree, that should be very clear. Okay, that the root node of the centroid tree represents the centroid of the whole tree. Its children represent how many subtrees will form if you remove the sorry, like how many different trees in the forest will be there if you remove all the edges which are linked to the original centroid in the original tree. So if you have a given tree and a centroid node C, if you remove the centroid node C, this T will get split into smaller subtrees T1, T2, T3, T4, so on. So in this case, it gets split into only two subtrees. So all of this is left subtree, all of this is right subtree, but the structure is different. So every node which lies to the left of, like every node which lies in this particular subtree of the centroid tree also lies in the same, like on the same side, like in the same subtree, in the in the same subtree of the given centroid in the original tree as well. For example, if you look at node 6, it lies in the left subtree of node 8 in the original tree, but node 6 will also lie in the left subtree of node 8 in the centroid tree. Okay, so this is a similarity basically, if you see. Okay, so let's come to the properties of centroidity like later on. But okay, yeah. So I think there are some more doubts. Uh, Cost to build we will discuss. Don't worry about it. Okay, Vedant is asking, do we do this to improve the worst case complexity of operations? Yes. Like we will show how this is useful and powerful. Like we will come to that. Don't worry about it. Okay. So like the next question is that is the centroid always height balanced? Yes, like we will also explain what height balance means, but yes, the height of the centroid is log n. Like we'll come to that. Don't worry. Okay, so I think like most of you, like most of the questions which people are asking are about the properties which we are yet to discuss. So let's come to that. And I hope that the procedure of forming the centroid tree from original tree, the overall idea is clear that what exactly is happening. It might take some time to get used to this, but like it should be very clear in your mind that the centroid tree is a very different representation from the original tree, and an edge in the centroid tree might not correspond to an edge in the original tree. Okay. Okay. So like now let's come back to the properties of the centroid tree. So the first property, a very basic and trivial one, is that the centroid tree contains all the end nodes of the original tree. Okay, and this is a very obvious property. Basically, that every node of the original tree will become a centroid of some smaller tree. And this could be a tree consisting of only a single node. Okay. So whenever a node becomes a centroid of that, like of a smaller component, it gets attached like to the centroid tree. So if you look at this example, like node 8 became the centroid in the first go. So therefore it became the root. Node 2 and node 9 became the centroids in the second iteration. So therefore their level is 2. I mean both of them like got attached in the centroid tree as children of node 8. Node 1, node 3, node 4, node 6, node 10 and node 13 became the centroid in the third iteration. So therefore all of their uh, levels is level 3. Like they all came at level 3 in the centroid tree. And similarly, like node 5, node 7, node 11, 12, 14, 15 became centroids of components which these are the single nodes. Because if you keep decomposing a tree, like whenever you remove a node, you get a forest. You recurse on that forest. For every forest, you get a centroid, you remove it, you again keep recursing. So you keep doing this till the time the forest contains only a single node, and then that single node gets attached as a leaf node in the centroid tree. So therefore, every node becomes a centroid at some point of time. Like be it a centroid of a tree which has only a single node. For example, node 7 became a centroid when the subtree had only a single node left, which was node 7 itself. So every leaf in the centroid tree will correspond to nodes which became centroids for like trees which had only single nodes. Okay. So is this property clear to everybody? Every node in it's a, and every node in Centroid in itself successfully after calling decompose. Yeah, I'm not sure what was the question, Shad, but maybe we can discuss it again. Okay, like doubts, like any other doubts so far? Yeah, so this is a very trivial property. I hope it's clear to everybody. So we move on to the next most important, another very important property of the centroid tree, that the height of the centroid tree is at most order log n. Okay, so this is a very interesting property that we we started with the original tree, which had some structure, and the claim is that whatever the structure of the original tree might be, like whatever might be the structure of the original tree, if you decompose it and form another centroid tree, if you decompose it and form another centroid tree, the height of this centroid tree is bounded by order log n. The height of this like the centroid tree would be at most order log n. Okay, and this is a very interesting property. So first, let's prove that why this is true. Sorry, and the proof is simple. That so what exactly are you doing? You are calling decompose on a given tree, find the centroid, recursively call decompose on the subtrees. So decompose T1, decompose T2, and so on. Decompose TK. These are subtrees of the original tree. And you keep doing this. And every time you call decompose on a level, like the height of the centroid tree is the depth of how many times you call decompose. Like the depth of this recursion is your height of this, height of the centroid tree. Because every time you call decompose, you create a new tree and attach it on the attach it to the centroid of the parent tree, basically. So if the given tree is T, you find centroid. Suppose it is the centroid. You call decompose on the two sides. Okay, I mean you call decompose. You find their subtrees, attach them as children to 8. So therefore, the height of this tree is the recursive depth to which you keep calling decompose. And the observation here is that every time you call decompose on a smaller subtree, the size of that subtree is less than half the size of the original tree. Why? Suppose given a tree T, if you are calling decompose on a subtree T1, okay, like you find the centroid, like find centroid and remove it, you get small subtrees T1, T2, you call decompose on them. The point is that by the property of centroid, like by the definition of centroid, every time you remove the centroid, the smaller trees which are formed have size less than equal to half the size of original tree. So therefore, size of T1 will be less than equal to half the size of T. Similarly, size of T2 will be less than equal half the size of T. So therefore, every time you recursively call decompose, the size of the tree on which you are calling decompose gets halved, at least halved. So therefore, this half, like this procedure can continue only for log n steps, because say the first time you call decompose, the size of the tree was n. The second time you call decompose, the size of the tree would be n by 2. The third time it would be n by 2 square, so on. And if you continue this in log n steps, in height 2 to the power log n, so 2 to the log n is n basically. So in log n steps, you will reach nodes where the size of tree is only 1. So size is 1. So and these will become the leaf nodes in the centroid tree. So therefore, the size of your centroid tree, I mean the height of the centroid tree is bounded by order log n. Okay. Doubts? Is this part clear to everybody? Like, are you guys still following? Yeah. So again, like it might take some time to get used to these ideas. Like we will also look at an implementation for the like for the problem and and get a better understanding. Yeah, so you can also think like this, that if like basically starting at the leaf and going up the like subtree size doubles, it is the same intuition, but this decompose intuition is better because like it matches well with what you are actually doing. That like like you are finding the centroid recursively calling decompose on the subtrees, and by definition the subtree size is less than n by 2. Like that is the definition of centroid, that if you remove it the subtree size will be less than n by 2. Okay, so it is a definition, and therefore every time you call decompose on a smaller subtree, the size of that subtree is less than half of the size of the original tree you started with. So you can keep doing this at most order log n times in depth. Okay. Okay, so like this is clear. So now again, like third property is also a very very interesting property. So what it says is that if you consider any two arbitrary vertices A and B and the path between them in the original tree, we can claim that this path can be broken down into two different paths, A to C and C to B, where C is the LCA of A and B in the central tree. LCA means lowest common ancestor. Okay. Okay, so this is a very very interesting statement. So I mean, what exactly are we seeing here? Like let's try to look to understand this via some examples. Okay, so suppose we look at node 1 and node 11, and we look at the path between node 1 and node 11 in the given tree. Okay, in the given tree. So in the given tree, what is the path between node 1 and node 11? Like this is the path, right? So this is the path between node 1 and node 11 in the given tree. What is the claim? That any path. So I mean we chose two arbitrary vertices A and B. Like 1 and 11 were the two arbitrary vertices we chose. The claim is that the path between them in the original tree can be broken down into A to C and C to B, where C is the LC of A and B in the centroid tree. So our A and B are node 1 and node 11. What is the LC of 1 and 11 in the centroid tree? 1 is here in the centroid tree and 11 is here. So the LCA of 1 and 11 in the centroid tree is node 8. Okay. So node 8 is the LCA of 1 and 11 in the centroid tree. And we claim that the path between 1 and 11 in the original tree, this path in the original tree can be broken down into path from 1 to 8 and 8 to 11. And the fact that we are looking at node 8 came from the fact that 8 is also the LCA of 1 and 11 in the centroid tree. Okay. So here I'm just trying to explain you the property, what exactly it is saying. Like I'm not giving any proof, or like all I'm showing you is some examples of what exactly are we talking about here. Okay. Is it clear to everybody? Like what exactly are we talking about here? Like should we maybe take one or two more examples? Like I mean, please do a thumbs up if you are following. Like it will really help me calibrate the speed. Okay. So it's not clear to some of you. Okay. Let's try to look at like maybe one more example. Pick any two. Okay, like I'll ask from you in the chat box, okay? The original tree has 15 nodes. Pick any two random nodes, A and B. The original tree has 15 nodes numbered from 1 to 15. We want to pick any two random nodes. Like Darshan said, let's pick 3 and 9, okay? So let's pick nodes 3 and 9. I don't even know where these two nodes lie. So like node 9 is here. And where is node 3? Node 3 is here. Okay. This is the path between node 3 and node 9 in the original tree. The claim is that this path can be broken down into two paths, path between 8 and 3 and path between 8 and 9. And where does this 8 come from? This 8 comes from the fact that the LCA of 3 and 9, the LCA of 3 and 9 in the centroid tree is 8. This is the LCA. LCA means lowest common ancestor. It means that which node is an ancestor, like which node is the lowest node, which is an ancestor of both the nodes A and B. Sorry. Again, I assume that most of you would know the definition of LCA. If you don't, then LCA just means that the lowest node, which is a common ancestor of both the given nodes. So the LCA of 3 and 9 is 8 in the centroid tree. And therefore, the path between 3 and 9 can be broken down into 8, 8 to 3, and 8 to 9. Okay. Even if you try to pick say some of the examples, suppose you say 7 and 5. What is the LCA of 7 and 5 in the centroid tree? The LCA of 7 and 5 in the center 7, 5. The LCA is 6. So 6 is the LCA. So I'm saying that you can break down the path between 7 to 5 as 6 to 7 and 6 to 5. And it is correct. Like like you can't do that basically. Okay. So this is a very interesting property. Yeah, so you don't have to see the path in the centroid tree. Okay, in the centroid tree, all you have to do is find the LCA of A and B. Okay, so like if we try to take one more example, say 2 and 6. For 2 and 6, what is the LCA of 2 and 6 in the centroid tree? LCA of 2 and 6 in the centroid tree is 2. So we are saying that the path between 2 to 6 can be broken down as path between 2 to 2, which is an empty path, starting and ending at the same node, plus the path from 2 to 6 in the centroid tree. I mean, this is just a way of telling that you can break down any path AB into two different paths. A path from A to C and a path from C to B, where C is the LC of AB in the centroid tree. Okay. You don't have to look at the path in the centroid tree. Like you just have to look at the LC of AB in the centroid tree. The path in the centroid tree does not have any relevance here. Only the LCA in the centroid tree have a relevance. And why is this always true? Like this is always true because the LCA of A and B for any two nodes A and B, okay, for any two nodes A and B, their LCA in centroid tree, their LCA in the centroid tree basically represents the first node which lies on path from A to B and was removed because it became a centroid. Yeah, apologies for the space. I hope it is still visible to most of you. So basically, I'm saying that in the original tree, the first time A and B got disconnected was when the vertex C was removed. And therefore, the path from A to B can be written as the path from A to C plus C to B. Okay. Like another way to look at it is that so basically what exactly is happening here is that suppose A and B were there in the original tree and there was some path. The claim is that okay, and suppose C is the LCA in the centroid tree. Some path B. Suppose C is the LCA of A and B in the centroid tree. Like this is the centroid tree and this is the original tree. So like what is the significance of the fact that C is the LCA of AB in the centroid tree? The significance is that when node C would have been removed in the original tree, in the original tree, when node C would have become the centroid and it would have been removed, this was the first node which disconnected A and B, or the removal of which caused A and B to go into separate subtrees. And why is that? Because, as I said earlier, like in the centroid tree, when you look at a node, that node represents the fact that it became a centroid in the original tree at this point. And every subtree in the centroid tree is formed by calling decompose on a similar subtree in the original tree, basically. So you you remove this node, it becomes a centroid. You delete the edges and you call decompose on these smaller subtrees. The fact that A lies in this subtree and B lies in another subtree is visible because A and B lies in different subtree in the centroid tree as well. So therefore, we can visualize that A and B would have been in different subtrees in the original tree as well when node C was removed. Okay, is it is it clear to everybody? Like I might be repeating the same thing again and again. It like if you're not following, say like if you might have missed a couple of sentences like of what I said in between, it might be fine because I'm just repeating the same thing again and again. Like I'm just trying to give to build that intuition of what exactly is happening here. Okay, like if you spend some time yourself and visualize what is happening, it would be clear like very soon. But to help you guys do that, I'm just repeating the same thing again and again. Okay, so I hope that it is clear. Okay, so moving on to the next property. Now, so if you notice what is happening is that we are basically decomposing the given tree into n log n different paths where every path starts at a centroid and goes to all the vertices which lie in the small tree for which this node is a centroid. Okay, and because of property 3, any path in the original tree can be represented as a concatenation of two different paths from this set of n log n paths. So any tree has how many parts? Like how many paths? A tree has n nodes. So it can have nc2, which is basically order n square paths. A tree can have order n square different paths. Okay. The claim here is that any path from this n square paths can be represented as a concatenation of two paths from a smaller set of n log n paths that we have processed, like that we know about. And this is the true, like this is where the true power of centroid decomposition comes into play. That you often have questions where you want to answer queries on paths, or you want to do some like some processing on paths, and there can be n square paths in the tree. But any path among these n square paths can be represented as a concatenation of two different paths from these n log n paths that we have processed. And this is where the true beauty of centroid tree comes into play. Okay. So again, like what exactly is happening here? The n log n paths come from the fact that like whenever we find a centroid node, we process all the paths starting from this centroid and ending at any node in the component for which this node is a centroid. For example, for node 8, we process the path from node 8 to 5, 8 to 6, 8 to 7, 8 to 2, 8 to 4, 8 to 3, 8 to 1, 8 to 9, 8 to 10, 8 to 11, 12, 13, 14, 15. So these are the 15 paths which we process for starting at node 8 and ending at any other node in the tree. Okay. So for node 8, we process 15 paths starting at node 8. Starting at node 2, how many paths we process? The path which starts at 2 and ends at 4, ends at 3, ends at 1, ends at 5, ends at 6, ends at 7. And that's it. Because node 2 became a centroid of this particular subtree, which had only 7 nodes. this edge had been deleted. So therefore, we process 7 paths for node 2, starting at node 2 and ending at any other node in the subtree. Similarly, for node 9, we process 7 paths because this component has 7 nodes. So any path starting at node 9 and ending at anywhere else, we process 7 paths. For node 1, like node 1 became a centroid of this small subtree, which has only a single node. So we process 0 paths. Or like maybe, yeah, I mean, like if you include the path which starts at a node and ends at a node, like the 0 length path, like then one path, otherwise 0 paths. It doesn't matter. Node 3, same thing, 0. Node 4, 0. Node 6. For node 6, we process the path starting at 6, ending at 7, and ending at 5. Because these two nodes were the only nodes which were in the component of, like which were in the tree at the time when node 6 became a centroid. Okay. So, two paths. Like for node 10, again two paths. Node 13, again two paths. For node 10, path starting at 10 and ending at 11, starting at 10, ending at 12. Similarly for node 13, two paths. And like these are all leaf nodes, so again zero paths. Okay. So basically, what we are doing is that at every level, we are processing at most order n paths. We are processing at most order n paths starting at every level. And why is so? Because any path is represented by the node at which that path ends. Because we know that a path always starts at the centroid and a path always ends at any other node in the tree. And every level has order n nodes, at most order n nodes, because the total number of nodes in your tree is order n. However, might you keep decomposing the tree, at any level, the total number of nodes that you process will be order n. So therefore, the total number of paths that you process at any level will be at most order n. Since your tree has log n levels, the number of paths you process in total are n log n. And these are the paths which start at a centroid and end at any other node except for the centroid. And if you notice, like this is the reason why we introduced property 3. Property 3 was that any path from A to B can be decomposed into a path from A to LCA and LCA to B, where LCA is the LCA in the centroid tree, or a node in the centroid tree, a node C in the centroid tree. So any path A and B is decomposed as a path from ending at A and starting at a centroid C, and a path ending at B and starting at a centroid C. And in property 4, we say that these two paths, the path starting at A and ending at uh, centroid C, and the path starting at B and ending at centroid C, both of these are part of the special n log n paths that we are processing, because both of these start at a centroid and end at a node in the component of the centroid. Okay, so a path which starts at a centroid and ends at any other node is part of the n log n paths that we have processed, the special n log n paths that we have processed. And therefore, any path from the n square paths which exist in a tree can be decomposed into a concatenation of two different paths, A to C and B to C, where both of these are part of our both of these are part of the n log n paths that we have processed. Is it clear to everybody? Yeah, because like Sudeepan is asking that processing a part takes n time, it becomes n square log n. No, like that is not the case. We'll come to that. Don't worry about the complexity right now of processing a path. Sorry. Yeah, so like this is basically the end of the topic. Like after this, we can move on to questions. So if you understand till now, we can start discussing some problems. Okay. I can also try to repeat property 3 and 4. Property 3 and property 4 are what forms the crux of centroid decomposition, of why centroid decomposition is so useful. Okay. So maybe I can try to quickly uh, discuss these two properties again. So some of you are saying that the property is not clear. So how many of you think that we should discuss the uh, the properties again? React with a confused emoji if you think that we should discuss the properties again. Okay. So, like roughly 51 people think that they understood like the properties, and 14 people are confused. So we also have some doubts. So maybe we can first look at the doubts. So like one doubt is that the edges in the centroids are not the same as edges in the original tree. Yes, that is correct. We don't have a correspondence between paths in the centroid and paths in the original. So whenever I talk about a path between AB, I'm always talking about the path in the original tree because every processing has to be done in the original tree. Uh, yeah, maybe I'll explain this again. Yeah, like how do you find centroid optimally? Like don't worry, we'll discuss that. Okay, so let's do one thing. Uh, okay. So what I'll do now is let's take an example of this particular tree, and let's write like I will write down the n log n special paths which we process, and then let's do some examples by hand that how any path query can be decomposed into concatenation of two special paths. Okay, so like when you call decompose on the original tree, 8 is your centroid. So you process how many paths? You process 15 paths. Like which of these are the 15 paths? The paths are 8 comma 5, 8 comma 2, 8 comma 1, 8 comma 3, 8 comma 4, 8 comma 6, 8 comma 7, 8 comma 9, 8 comma 10, 8 comma 11, 8 comma 12, 8 comma 13, 8 comma 14, 8 comma 15. Okay, so these are the 15 paths that we have processed. Have I missed something? Yeah, like there are 14 paths which we have processed actually, 14 paths because the path starting at 8 and ending at 8 is uh, a zero in part. Okay, so this is at the first step. Then we decompose into T1 and T2. For T1, we process another six paths, which will be 2 comma 5, 2 comma 1, 2 comma 3, 2 comma 4, 2 comma 6, 2 comma 7. For T2, we will process 9 comma 10, 9 comma 13, 9 comma 14, 9 comma 15, 9 comma 11, 9 comma 12. Okay, so we processed six paths each on in T1 and T2. For the centroids 2 and 9, we are processing paths which start at a centroid. So all the paths which start at 2 in T1 and all paths which start at 9 in T2, we have processed. By processed, I mean maintain some information. Like we will look at some examples. For example, just maintain the distance, for example. Okay. Suppose you want to compute the distance between any two paths. Like you can process these special paths and compute their distances and then answer any query quickly. Okay. After decomposing two, I have 1, 3, and 4 as individual subtrees. We don't need to process anything here. In this particular subtree, like let this be called T3. I process 6 comma 7 and 6 comma 5. Okay. And let this be T4, T5. In T4, I process 10 comma 11, 10 comma 12. In T5, I process 13 comma 14 and 13 comma 15. Is it clear to everybody? Like which paths I am processing? Which so these are the set of n log n paths which I am processing. Okay, these are set of n log n paths which I am processing. Why n log n? Because the centroid tree has log n levels. At each level, we can have at most order n paths, ending at a particular node. Because at each level, the maximum number of nodes we can have is order n. Okay, so these are the n log n paths that we are processing. Now, give me any query. Like let the query be given two nodes, find the sum of uh, the edges which lie on path of these two nodes. Okay, give me any query. Yeah, so suppose Prashant is saying 13 comma 7. So if you look at 13 comma 7, this is node 13 and this is node 13 and node 7. Okay, so you want to find, like suppose the question is find the distance between 7 and 13, and I have the distances of the paths which have been processed. These are the processed paths. I have the distances of these paths. Okay, now for 13 and 7, this is node 7, this is node 13. What would be the LCA in the centroid tree? We don't even have the centroid tree in front of us, but we know that the LCA will be node 8. If you come back and you look at node, if you look at node 13 and node 7 and node 13, their LCA is node 8. Okay, so we know that node 8 is the LCA. So this means that we should look at the set of processed paths which start at node 8, and we will find a path 8 comma 7 and 8 comma 13, 8 comma 7 and 8 comma 13. We will definitely find it in this processed path set, and we can use it as it is. And if you see here, we have a 8 comma 7 and we have a 8 comma 13. So we can just do equal to distance of 8 comma 7 plus distance of 8 comma 13. And this distance is pre-computed because this is the part of our initial pre-processing. This is the part of our initial pre-processing, that we are pre-processing these order n log n paths. For these n log n paths, we are maintaining some information. In this case, the information is distance. It could be something else. For example, the next question is, what is the minimum weight path on, suppose I ask you the minimum weight path on the path which, like the minimum weight edge which lies on path from 13 to 17. The answer would simply be min of the minimum weight edge from 8 to 7, comma, the minimum weight edge from 8 to 13. Because we know that these two are disjoint paths whose concatenation will lead to the original path. This is the property of the centroid tree, that the n log n paths you have processed. By processing, I mean that you can compute their minimum weights, you can compute the distance, you can compute any function f, like given some properties of the function f, any function f that you want to compute for 13 and 17, and which can be computed by combining the answers, of smaller paths, of smaller disjoint paths. So f of 8 comma 7 and f of 8 comma 13. You can do this, and you can answer any query involving a function f by pre-processing the f values only for n log n paths. You can answer any query between two nodes xy by preprocessing them for n log n paths only. Okay, is this more clear now? Like, does it make more sense now? For people who had doubts earlier, like, is it better now? Like, do you have a better understanding now? Okay, great, great. Yeah. So now I think it is time to move on to problems and maybe also look at some implementation, like some code, because it looks like a lot of complex things are happening here. So it might be hard to implement it via code. But yeah, like I want to show you that how easy and how simple it is to implement, and like really help you guys appreciate the beauty of this concept. Okay. So the first question is a toy problem. This question does not need centroid decomposition by any chance. The question is just that given a tree with n nodes, you are given q queries, and each query is of the form u comma v. That given two nodes return the sum of uh, elements, like or the sum of edges on the path from u to v. Compute the distance between u and v. So normally, what you would do is you would compute the LCA in the original tree, and you will do distance from node U to LCA plus V to LCA, right? But you want to do this via centroid decomposition, and this is the same as what we discussed here. This is same as what we discussed here, that we can decompose any path into a path going via the centroid, which is pre-computed, and we can add the distances which have been pre-computed to find the distance of the path. Okay, so step one is do centroid decomposition and pre-compute this distances array. And the second part is that you find the LCA of UV in the centroid tree, and the answer will be the distance from this LCA to U plus the distance from the LCA to V. Okay, like let's look at the code once. But is the problem statement clear? Like, does anybody want me to spend more time on the problem statement? I think we've already spent enough time discussing this. So is the problem statement clear? That like what exactly is happening? Any doubts so far? Okay, great. So now I'll show you the code. Yes, the question is that you will have m queries, and in each query you will have to return the distance between the nodes x and y, which are given in that query. Like, that is the question. This is a toy problem, just to show you the implementation of centroid decomposition and how it can be very useful. Okay. Okay. So let's move on to some code. Uh, okay. Is everybody able to see the screen? Like, do you guys want me to zoom in further, or is the code visible? Like, is the code readable? Okay, great. Okay, so like this is my main function. I input n, which is the number of nodes in my tree, and then I input n minus one edges. N minus one edges. So yeah, there can be multiple ways of implementing this. I'll show you my way. I think this is an efficient implementation. If you think otherwise, I'll be happy to discuss it with you. But uh, yeah, I'll be discussing my particular implementation. This is how I generally implement central decomposition and in general like graph problems. So yeah, I'll keep explaining you. Like this is a hybrid combination of an edge list and an adjacency list. So what I'm doing here is that to read and to like I have three arrays U, V, and W, which represent an edge. So for the ith edge, the ith edge goes from U of I to V of I and has weight W of I. Okay. So while reading the ith edge, I read these edges into U, V, and W global arrays. So U of I is the starting point of the edge, V of I is the ending point of the edge, and Wi is the weight of this edge. And yeah, I mean this is just the problem had zero based indexing. I prefer one based indexing, so I've done a plus plus. And then to insert these edges into my graph, what I do is that in U and V, in the adjacency list of U and in the adjacency list of V, instead of pushing back the adjacent vertex, I push back the adjacent edge number. Okay, so ith edge number I is the ith edge. So in G of U, I push back I. In G of V, I push back I, and I is the edge number. Okay, and if I have the edge number, I can easily identify the starting point, ending point, and the weight of the edge by looking at UI, VI, and WI global arrays. So this is just the part where I take input of the graph. then I call my decompose function. The decompose function is responsible to compute the centroid decomposition and do any pre-processing that might be required. Okay. Uh, yeah. Any doubts by any chance? Yeah, I'll share the Discord. I'll share the code in the Discord as well. Okay. Uh, sorry. Okay. So then I call my decompose function. Like the decompose function is responsible to do the centroid decomposition. I call the decompose on node one. This is an arbitrary node. I have one base indexing. This is an arbitrary node on which I call my decompose. You can choose any node. And initially, the parent is set to -1. The parent is basically the centroid of the centroid of the tree which was decomposed before this step. So it will become more clear of what the parent represents. So NN is yeah, I mean it's bad naming probably, but NN is the size of the subtree on which this decompose is being called. On the first call of decompose, the size would be equal to n, the given input n. But like when you call decompose on smaller subtrees, it could be a it could be a smaller number. So I do a DFS to compute the subtree sizes. So I root my tree on node 1 and I do a DFS to compute the subtree sizes. So my DFS 1 is nothing. It just, yeah, the subtree size of u is 1. I increment my NN, which is a global variable, to count the number of nodes which lie in this subtree, which I am iterating on. And then I iterate on the adjacency list. So remember, G of u had a list of all the edges which lie adjacent to u in the original tree. So I iterate on all the adjacent edges. I get the vertex which lies on the other end of this adjacent edge. So if u lies on one end of edge E, W is the vertex which lies on the opposite end of edge E. And I have this small utility function called adjacent, which takes in a node and an edge which is adjacent to this node, and it represents the opposite vertex. So one of UE and VE are the two endpoints of edge E. One of them have to be equal to X. The other one is returned by this function. Okay, so I get the adjacent vertex. I check whether the adjacent vertex is equal to the parent. If yes, ignore it. If no, I check whether the adjacent edge has been deleted. So remember that during while doing centroid decomposition, we often have a need to delete the edges. Like whenever we find the centroid of the tree, the next step is to remove that node, delete the edges, and then uh, like recursively call decompose on the smaller subtrees. So instead of actually maintaining a data structure like say set or uh, a hash map or a set or something like that to actually delete the edges, I simply maintain another global array called deleted, and I mark an edge to be deleted. I just say an edge E is deleted if deleted of E is 1 or 2. Okay. So to check whether an edge E has been deleted or not, I just check whether the deleted value for that edge is true or false. So if the edge has not been deleted and if the adjacent vertex is not equal to the parent, then recursively do a DFS on that adjacent vertex and compute its subtree size and add its subtree size W to subtree size of U, because subtree of U is subtree size of U is 1 plus subtree size of all the children. So this is a very standard way of doing a DFS on a tree. I'm probably explaining way too much than is required here. Okay, so I compute subtree sizes and number of nodes in this tree by doing a DFS. Now I need to find the centroid. To find the centroid, I do another DFS. I've just renamed this function to find centroid, but this is basically just another DFS. So the find centroid is also a very simple DFS function which starts exploring a node U, look at all the adjacent edges. If an edge is deleted, ignore it. If an edge is not deleted, then look at the adjacent vertex. check whether the adjacent vertex is not equal to the parent, and whether the size of the adjacent vertex is more than n by 2. Here I'm doing nn by 2 because the nn represents the size of the tree on which we are currently doing centroid decomposition. Like it could be a subtree in the recursive call as well, right? So I check whether the subtree size of w is more than nn by 2. If it is more than nn by 2, it means that the centroid lies in the subtree w. So I call find centroid on w, and I directly return its value. So notice that from a given node u, you can do this recursive DFS only on a single child w, because as soon as you call find centroid on a child w of u, you return its value. So you return from this function. I mean, this loop is broken. Okay, and this is working as expected, that only one child can have a subtree size more than n by 2. And if no child has a subtree size of more than n by 2, it means all children have subtree sizes less than or equal to n by 2. It means that node u is a centroid itself. So just return the node u. So this is a very simple DFS function, also works in order n, to find the centroid of the tree. Once we have the centroid, we want to do construct the centroid tree. So in terms of constructing the centroid tree, what we need to do is we need to add the edge from P to centroid in the centroid tree. So I have this function called add edge in centroid tree. This function basically can be different for different questions depending on how much information you need to maintain. For this question, it is just enough to maintain the parents. So I mark the parent of the centroid as P, which was the centroid of the previous component, and I mark the level of the child as level of parent plus 1. I'm maintaining levels and parents. Okay, like the level is the level of a node in the centroid tree, the parent is the parent of the node in the centroid tree. Okay, so this information is maintained for the centroid tree and not for the original tree. Once this is done, I need to process the order in paths which start from this centroid and which goes to all the leaves in this component. Okay, and to do this processing, I do another DFS. I do another DFS, and the trick here is that to store this processing, instead of storing an n square array from distance, so I could have also done something like this, distance of n cross n, where distance of ij represents distance between node I and node j when node I becomes a centroid, right? Like this is the special path which you want to process. But because of this condition, when node I becomes a centroid, there are a lot of entries in this n square array which will be empty because the number of different paths are just n log n. Okay, so instead of doing this, I actually maintain a dist of log n comma n, and it means distance of level comma x would be distance of distance between c and x in the original tree when node c becomes a centroid at level. Okay, so basically whenever a node becomes a centroid, it has some level in the centroid tree, and we know that any node x can be at any level, a node x can be only in one of the different components. So if you look at this image, you see that at level 1 there are two centroids, a centroid 2 and centroid 9, but any other node in the tree can be either in the component of level 2, can be either in the component of centroid 2, or can be in the centroid of or can be in the part of centroid 9, but not both. So when I talk about the distance of a node at a particular level, I already know which centroid I'm talking about, because at any level, a particular node can be under the component of only one single centroid. So if I specify the level, I have specified both the information, the centroid which I'm talking about and the node which I'm talking about. Like the distance, like I want to compute the distance between the centroid comma node. So instead of specifying the centroid, I'm actually specifying the level, and therefore I'm maintaining a distance of log n comma n distance array. Okay. So if you look at the DFS2 which processes uh, the paths, in the DFS2, I'm routing my tree at centroid and I'm passing the level of the current centroid. And in my DFS2, I do a standard DFS where I compute the adjacent vertex. I check whether the edge is not deleted and whether the adjacent vertex is not a parent. If it is continue, otherwise, the distance of node W at this level, like at the level which I've passed, the distance of node W at this level is equal to distance of node U at the level plus the weight of the edge. And recursively do a DFS on W, U with level. So the idea is that every node W can be under a single centroid at a given level. So if I have specified a level and a node, I already know which component I'm talking about, because a node can only be in a single component at a particular level in the centroid tree. Okay. So this is also, I mean, these are very, very small implementation details which make it really efficient to do the implementation. Okay, like you can also try to spend more time yourself on this code and understand these technical details, but the idea here is that like we want to make the implementation as efficient as possible, and these are the small automations to do that. I mean this DFS then computes our distance array, and once we have done the pre-processing, we move on to the decomposition part, that we iterate on all the adjacent edges and we delete them and recursively decompose the adjacent subtrees. To do that, again, I iterate on the edges which are adjacent to my centroid. If the edge is already deleted, I continue. If the edge is not deleted, I delete the edge by just marking it deleted. So I mark delete equal to 1. I find the adjacent vertex, sorry, and I call decompose on the adjacent subtree with the current centroid as the parent. So the idea is that whatever centroid tree is formed by calling decompose on the smaller subtree, that uh, like that small centroid tree should be attached as a child to the current centroid. Okay, so therefore I pass the current centroid as a parent. This is how the decompose function works. Doubts so far? Doubts? Yeah, I mean the adjacent function is yeah, it is a, and sorry, yeah, it is an implementation detail. So adjacent function is basically just, so if you look at how I am representing my edges, in my G of U, I'm storing edge numbers. I'm storing a list of E1, E2, E3, so on. And these are edge numbers. Like, these are not adjacent vertices. Usually you store, like usually you do this, that in adjacency list of U, you store V1, V2, V3, the adjacent vertices. But I'm not doing this. I'm not doing this. Like what I'm doing is that in the adjacency list of U, I'm storing the adjacent edge numbers. So from a given node, comma its adjacent edge number, I need a way to find the adjacent vertex V1. Given a U comma E1, I need to find the vertex V1 which actually lies on the opposite end of edge E1. So to do that, I use the adjacent function, which takes a node and an edge number adjacent to that node and returns the opposite vertex. And it does so by doing this. Like I just take a XOR of UE, VE, and X. One of UE and VE should be equal to X because one endpoint of E is X. That is the assumption. So the XOR will cancel out, and what will remain is the other endpoint. This is just an efficient way of avoiding an if else. Any other questions? Yes. So U is the start vertex, E is the end vertex, and E is the edge number, and adjacent function gives me the opposite end. Yeah. So the distance array again. So uh, like I want to compute now. Once I have found a centroid, I want to compute the distance of this centroid from every node which lies in the component of this centroid. Okay. To do that, I can either maintain, say, I mean, I can either do a dist of n cross n. I cannot do this because n is very large. So I can rather do a vector int dist n, where like whenever a node becomes a centroid, I push back. Like whenever a node becomes centroid, I do a pushback with say, or yeah, I mean I could also do a set int distance, where like whenever like, or maybe sorry, yeah, unordered map, maybe, yeah, yeah, I could do this basically, that whenever a node becomes a centroid, I look at all the NN nodes which lie in the component of centroid. For all these NN nodes, I can compute the distance of centroid comma x as some value, right? I can compute this. Like this would be the straightforward way of doing this. But the point is that I'm maintaining an inefficient data structure, an unordered map or a map. Like this is very inefficient. And second, like I need extra information here. The point is that I can also represent the same information by only maintaining a distance of log n comma n. Why? Because I know that the height of my centroid tree can at most be log n, and at every height, a single node will have a single distance, because a single node, like every height so if I give you a level comma x pair, I can find centroid from this. Like there's a one-to-one mapping between a level comma x pair and the centroid which I'm talking about. Like the centroid comma x distance pairs can be replaced by, so basically what I'm doing is that I'm replacing centroid comma x, I'm replacing by level of centroid comma x. And this helps me maintain a single log n comma n 2D array, such that I can save the distance between a centroid and a node x as a level of centroid comma x, because this mapping is one to one. Like the centroid comma x mapping is like with the level centroid and x mapping is a one to one mapping, and therefore I can actually do this. Again, this is an implementation trick. I would like, if it's not clear at the first time, don't worry about it. Spend some more time on the code. Try to look at the examples and understand what is happening. I'm sure you'll get it. Like, of course, like I'm showing you the most efficient implementation which I have evolved over say 4 years of my practice. Like, I don't expect you to come up with this implementation the first time you go and try to implement it yourself. But the whole idea of having these sessions is that like you guys can directly benefit from the experience which I have, right? So like I'm giving you the most efficient implementation which I know of. You can spend some time understanding this and then appreciate it and then start using it and maybe further improve it in your journey. Okay. So yeah, like this is the whole idea of maintaining the distance array. But a distance of level comma x just maintains, like just represents this, like the distance of a centroid from a node x. Okay. So this is the decompose function. Moving on to the compute distance. So like once we have done the decomposition, we start reading the queries. Okay, okay. Any other doubts? Yeah, I would like we are running out of time, so I will like suggest you guys to like maybe like spend some time working out the examples yourself to understand it better like after the class. So like once we read the queries, like we read two nodes x, like we scan two nodes x and y, and we want to compute the distance between x and y. I'm using a one-based indexing, so I pass x plus 1, y1, like y plus 1 to my compute distance function. In the compute distance, I have two nodes x and y. I want to compute the distance between these two nodes. Now, the first thing to do was to compute an LCA. Like we need to compute the LCA xy in the centroid tree, right? So now some of you might know that there are complex methods of computing LCAs like binary lifting and stuff. But the beauty here is that the height of centroid tree is only log n. So even if you just manually iterate, you don't do any pre-processing and you just do an iteration manually. Uh, yeah, I'm like by manually I mean that like you just keep iterating from like you start from nodes x and y and you keep iterating up based on the level of the nodes and you finally reach the LCA. Like you reach the node like if this is your LCA and you want to reach here, like you just keep iterating. Even then, the complexity would be order log n to find the LCA. You can do more advanced pre-processing and maybe reduce this to order log n or maybe order 1 as well, but it's not required. Like order log n is good enough. So you just do an iteration. Well, and how do you do the iteration? You say your I is equal to x, j is equal to y, and you keep iterating till your I is not equal to j. So till the time both the nodes don't become equal, you keep iterating up. Again, like this is a slightly complex for loop where I've incorporated a lot of things in a single loop. I can also expand it and write it as a more complex, like more easier to read while loop with a lot of if and else conditions. But yeah, I prefer to do it like this. So like you start with I and j as x and y. You keep iterating till your I is not equal to j. And the condition to iterate is that if your level of like whichever node has a deeper level. So if your level of I is less than level of j, it means your node j is deeper than node I. You make j is equal to parent of j. Otherwise, you make I equal to parent of I. So whichever node among the two is deeper, suppose this is a deeper node, you move it one level up, and then you again compare. If they are the same level, you move up any one of them. So the idea is that you keep moving the two nodes like up like one by one till you finally hit the LCA, and yeah, like you basically find the LCA. And in this for loop, like this for loop will basically take order log n time and give you the level at which the LCA is there. Instead of giving you the actual node number, I just want the level of the LCA. Like I'm just doing LCA of level is equal to level of I because I will eventually become LCA. So I have the level of LCA instead of the actual node because I don't need the node. Like that is why I like that is the reason I computed the disk sizes because I don't need the node number. All I need is the level. Once I have the level, I know that distance of LCA level comma x will represent the distance between x and the actual LCA node. Similarly, like distance of LCA level comma y will represent the distance between y and the actual LCA node. So I just yeah like I just use these pre-computed distances and add them and return them basically. So like this gives you the final distance between nodes x and y. Okay, so like I mean this function works in log n and this was super easy to implement, like just a single for loop or while loop. Okay, so this is the general template of centroid decomposition, which you can use for other ones as well. That you have a decompose function. This part is standard for every question. You probably want to do a DFS to compute subtree sizes. Find the centroid. Once you find a centroid, you want to do some pre-processing. This part of actually doing the pre-processing varies from function to function. But once you have done the pre-processing, like this part of actually iterating on the adjacent edges, deleting them, and then recursing also is standard across all problems. Okay. So when I initially started like coding centroid decomposition, I used to use a set of like I used to represent my graph as a set, like so that I can easily insert and remove nodes to simulate this edge deletion. But this method works much better and is much faster because instead of actually doing any deletions which are costly, you just mark it as deleted and just maintain another boolean. So yeah, like I mean this has been improved over years of practice, and I'm giving you the most distilled version. So don't, uh, yeah, I mean don't worry about the implementation too much. Just try to spend some time on the code and appreciate it, uh, like after the class. Okay, doubts. Yes, definitely we can implement it the same way. Like the only thing, if the so right now the weights were on edges. If the weights are on nodes, then all that would change is that in this function we are computing the distances here. I'm adding the edge weight. Instead of adding the edge weight, I'll probably add the weight of the node W on which I'm recursing. Like that is probably the only thing that will change. So only a single line will change, and the rest everything will work as expected. I don't know what is the mirror tree problem, but like you can see. Any special problems to practice? Yes. So we will be uploading some problems. The total complexity is n log n. So can we still use set? You can use set, but the point is that in case of a set, the constant factor is very bad. So yeah, it is just more efficient to avoid complex structures. So yes. So okay, coming back to the agenda. Sorry. So coming back to the agenda for today, like we have discussed this question, we also seen implementation. I had two more problems in mind to discuss, which I had written in these slides. Okay, I don't think we have enough time to go over these problems today. We only have a few minutes left. So, like maybe I'll so this is my blog on Centroid Decomposition. I originally post this blog on Quora, and then I also have like the same blog on my own WordPress. I would say like I'll share the slides on the Discord group. I would suggest you all to go on this blog and maybe like read over the blog again. There are also some links to some problems which you can practice for this concept along with accepted codes which you can take a look at for better like for the better understanding of the topic. Okay. Uh, this can be used to solve a wide variety of problems. Like I wanted to discuss a few more problems, but I don't think we have enough time today to do that. So tomorrow I had like originally I had scheduled a lecture on segmentary beats, but now I have modified that class. I think it would be better if we continue discussing centroid decomposition because there is also a concept of persistent centroid decomposition. I kind of invented that idea like I prepared a problem like a div1 e problem on code forces where that concept is being used, and it is also I think a very beautiful concept. So it's better that we discuss persistent centroid tomorrow. Like there's also not much resources. Like there's only the blog which I wrote, which is there the concept, and I haven't seen it used much. So it would be better if we discuss that. So instead of discussing segmentary beats, I have modified tomorrow's lecture to I have modified tomorrow's lecture to discuss centroid decomposition instead. So we will discuss persistent centroid decomposition tomorrow. For segmentary beats, I think there's already a blog and also like videos by Ericto and others who have tried explaining it. I'm sure like you'll find some useful resources. But for persistent centroid, I haven't seen any like widespread resource apart from my own blog. So I think it would be like it would be a better value addition if we discuss persistent centroid tomorrow. So I have modified tomorrow's class, and yeah, I can probably share resources for segmentary beats. You can take a look, and yeah, later on maybe in uh, some other camp or like some other free class, I can conduct on segmentary beats. So I also plan to start a course on segmentaries in general on Unacademy, and I was so like there I'll be discussing all sorts of like I'll start from the basics and I'll discuss all sorts of advanced tricks on segmentaries. Like maybe I'll try to keep like in the end of that course, I'll probably also discuss segmentary beats. I'll probably try to keep the lectures on segmentary beats free so that they're accessible for everybody. And maybe like if people are interested into like in learning more, like in looking at all the courses, then like you can also maybe opt for the paid subscription. Yeah, it's really up to you. But yeah, like instead of segmentary beats, we will be looking at persistent centroid decomposition tomorrow. So I've changed that slightly. Also, apologies for anyone who really wanted to learn segmentary beats, but we won't be having that lecture tomorrow. Hopefully, again soon. But yeah, do spend time on this. Like you won't be able to appreciate persistent centroid if you don't understand centroid decomposition. So please do try to spend some time like maybe today evening or tomorrow morning on revising this. I'll also start tomorrow's lecture by maybe discussing a few easier problems on centroid decomposition, like so that we have a better understanding of centroid decomposition before we get into persistent centroid, and then we will like start looking at a problem of persistent centroid, motivate the idea of why it is needed, and then maybe build on top of it that how we can actually achieve persistence in centroid and what kind of problems can be solved by having that ability. Okay, so that will be the schedule for tomorrow. Yeah, I think that's all I have for today. I'll share the slides on Discord in case like there'll be TAs to help you out. Like some of the TAs were also active in today's chat. I fully understand that it might be too much to absorb. Like this is like Centroid is a complex topic. I originally learned it by uh, looking at Peter's blog. Like Peter Metrigev is a very famous computer programmer. So he mentioned this idea on his blog, and there was like this small paragraph, and I had to spend I think 2 weeks on that single paragraph to fully grasp this topic. And at that point of time, like there were not much resources available online on this topic, so therefore I went ahead and wrote that blog, which I think became quite famous. So like this is a complex topic, but once you start appreciating it, I think it really gives you a lot of power to solve a wide variety of questions. And like even problems which people solve via HLD or like other advanced graph tricks can be solved by Centroid as well. So like this is a very useful topic which has very diverse applications in solving problems on trees specifically. Okay, yeah, I think that's all for today, and see you guys again tomorrow, or maybe in a couple of hours if you guys are also attending some Div 2 classes. Yeah, I have a Div 2 class in 1 hour. I'll be discussing Moore's algorithm, and I'll also discuss Moore's with updates. Uh, it got like so basically the class is on square root decomposition. In case some of you guys are interested, you can join that as well. Thank you guys. Have a good day. Bye.